So we did a review of soil mechanics. So we're starting other stuff, ground improvement and modification. So be attentive to follow the lecture. Okay, let's start. So usually when we are dealing with a construction area, sometimes the soil is not suitable to support structure totally. Why? The load from the structure is transmitted to the soil. And sometimes if the soil is not suitable to carry that load, there will be excessive settlement, there will be excessive bearing capacity failure. Examples such as granular soil may be very loose. If they're loose, they may indicate large settlement. Let me ask you, why do you think loose soil have very large elastic settlement? Why do you think loose soil will produce large elastic settlement? Anybody? Anybody? Why do you think they'll produce large elastic settlement? Why? Okay, and we also know that, okay, fine. If they're loose, they need to be densified to increase the unit weight and shear strength. No. Consolidation is a different thing, Alfred. Consolidation occurs in fine-grained soil. We're talking about loose granular soil. Consolidation settlement will occur on saturated fine-grained soil. Okay, Kahura, a little bit, yeah. High number of voids which are incompressible. That's true. That's true. But the truth is, loose soil have very low elastic modulus, very low elastic modulus, very low elastic modulus. Now, when you densify the soil, the elastic modulus increases. Of course, you're reducing the voids, but the elastic modulus does increase. Now, in most cases, the soil is undesirable and must be replaced. Yeah. Now, Humphrey, now this is the point I'm talking about. Soft, saturated clays will experience consolidation settlement. Soft clays. Okay, so consolidation settlement occurs on saturated fine-grained soil. Do you understand how the process of consolidation takes place, Alfred? Since you brought this up. Alfred, do you understand how the process of consolidation takes place? Okay. Now, first of all, for consolidation to take place, the fine-grained soil must be saturated. So when you apply loading to that soil, all right, it increases the pore water pressure. the loading is taken by the water, it increases the pore water pressure. Now, because the fine grained soil has very low permeability, it takes time for the water to squeeze through until the pore water pressure dissipates. That's the process of consolidation. That's the process of consolidation. All right, we'll learn more as we go on. Now, like we may face a couple of problems with very loose soil or grounds that are not good. Some of the problem will be bearing capacity failure, large total and differential settlement, instability of slope, liquefaction, more so in loose sands and silts. Your problem with liquefaction and seepage problem. Now, the possibility what we can do, either we can avoid these sites only if there's alternative land. Design superstructure accordingly to transmit load to the superstructure and remove and replace problematic geomaterials, and then try to improve these by other techniques. So we have 5 major categories of ground improvement. Soil improvement without admixtures, coarse grain. Soil improvement without admixtures, fine grain. Soil improvement with replacement. Soil improvement with grouting, admixture. Soil improvement with inclusion. So when we talk about with inclusion, we're talking about mechanically stabilized earth walls, okay, or geosynthetics, reinforced earth walls, okay. So mechanical stabilized earth walls are earth walls with reinforcements in them. They can be metallic reinforcement, which is inextensible reinforcement, or geosynthetics, which is extensible reinforcement. So we're going to do a couple, and probably for MSc walls, we will probably push that to the topic of geosynthetics. We push up the topic of geosynthetics. Let me pause and see if you have questions. Let me pause and see if you have questions. Any question, ladies and gentlemen? Any question, ladies and gentlemen? Let me give you time to ask questions. Yeah? So far, so good. Okay. Now let's see. Now, the reason why we doing technique is sometimes we have problematic soils. Okay. Now, the problematic soil may be natural or feed. Okay. Natural soils such as soft clay. Soft clay have very low strength, very high compressibility, and low permeability. Okay. Now, silt clay, silt soil have very low strength, high compressibility, and high liquefaction potential. High liquefaction potential. You know what liquefaction is? Liquefaction is a phenomenon where if loose, saturated soil, you apply loading that, the pore water pressure will increase. The effective stress reduces. As the pore water pressure continues increasing, the effective stress reduces. When the effective stress reaches zero, soil loses its strength completely and begins to flow like a liquid. Okay, that can be caused by earthquake. That can be caused by ground shaking due to pile driving. It can cause liquefaction. Now, organic soils are very high compressibility and large creep deformation. Okay, loose sand also have a problem with high liquefaction. Okay? Expansive soils like expansive clay, okay? They have high volume change, shrinkage when there's no water, and it expands when there's water. That will be the next topic where we deal with the problematic soil. And we'll only deal with two problematic soil, expansive soils and collapsible soil, like loess, okay? Very high collapsible soils. We will deal with that as in the next topic. Okay. So we have a lot of soil improvement techniques, okay? And we will only cover a portion that we think okay, I'll give you that page. I'll give it to you if you need it. Okay. I just include that in the last minute. Well, I'll give it to you. So we will cover just a portion of this so that we may appreciate how this will be done. So we have lots and lots of ground improvement technique without admixtures, with admixtures, so many. Okay, we'll just cover a couple of these. Others you may be able to read by yourself or study by yourself, probably in the course of your practice as an engineer. Okay. And by the way, you have students here that are practicing, right? That are working, right? They might have come in as mature entry students. All right, okay. So let's see. So let's start with the soil improvement admixtures, okay, in constant soil. So we have major methods: compaction, dynamic compaction, and vibro compaction. Okay, so let's change this vibro compaction. Okay, I'll change that later. Now, compaction is just the shallow densification of soil deposit. Shallow densification of soil deposit. We may use rollers, either static rollers or vibratory rollers. So we use static roller, sheep foot roller for fine grained soil, and vibratory rollers for coarse grained soil. Okay. Why do we use static rollers or sheep foot rollers for fine grained soil? The reason is, okay, it tends to knead the soil together, knead or mold the soil together. Now, for fine grained soil, no, for coarse grained soil, we need to somehow densify the soil together. So we need to give it a vibratory movement to make it compact. Okay. For dynamic compaction, okay, because of you want to compact as much depth as possible. Okay, so in this case, we drop a weight. Weight will be typically 30 to 50 kilonewton, dropping at a height of 30 meters. So this is suitable for compacting coarse grained soil and then compacting deeper depths. So let's have a look at this. Okay. Let's start with the compaction. Now, compaction starts from the lab. Okay. You did compaction in year 3. I think topic is soil mechanics year 3. Now, it starts from the lab. Now, in the lab, we try to catalyze the soil either through standard compaction or modified compaction. Now, when we do compaction, we try to define the maximum dry density and the optimum moisture content of the compaction curve, that plus zero air void ratio. So in this case, we have, look at this curve. Okay, look at this curve. We have different zero air void ratio plotted for different specific gravity. Okay. Oh, sorry, for different saturation. So for different saturation. So, which of these zero air void ratio? Okay. So now let me know. Just put that. Okay. There will be a zero air void ratio around. Okay. This guy should have done a better job. Okay. Different saturation. Okay. Let me just do that to avoid so many problems. So you define the optimum water, so optimum dry, the maximum dry density and the optimum water content. The optimum water content. Now, the question is, what's the difference between standard and modified compaction? You learned this. What would be the difference between standard and modified compaction? What would be the difference between standard and modified compaction? Let's have some discussion. What would be the difference between standard and modified compaction? No, the mold size is the same somewhere. Weight and length of the draw farmer, yes. Okay, so Kiara's, you say that standard is for light, modified is for heavy. All right, so explain further. Okay. Mold size is the same on tour. Well, there are a couple of people typing. I'm just waiting for them to type. The weight of the Rama, yes. So I think Thomas already talked about weight and the length. Okay. So Samuel says 5 layer for modified, 3 layer for standard. That's true. Number of layers, yes. Now, Samuel, and I think Bwahi, Thomas, and Karime Jerry, Samuel, Karime, Boati. You're right. Okay, you're right. So you gave, okay. Now, marry together your point. 1 point. Marry together that. Thomas, Samuel, Omondi, Karime, Jerry, and Thomas Boati. What you've told me is right, but marry together. Okay. If you marry together, number of layers, different number of layers, different um, uh, different weight of the hammer, okay, and difference in the drop height, okay, it gives you different compaction energy. Okay? Difference in compaction energy. So in other words, the modified will give higher compaction energy than the standard compaction energy. Now that brings me to what who said, somebody here, brings me to what Kaira Francis is saying. Standard is for light compaction, modified is for heavy compaction. Now, we use standard compaction in places where we anticipate very high loading, like when we will compact subgrade for airport runway, or sometimes for roadway. Okay, but if I don't anticipate any heavy loading, I will not use modified. I'll use standard compaction. So the difference is the compaction energy. Okay. Now, once a standard compaction criteria field in the lab, okay, you need to specify range of values in the field. Usually, you will specify between 90 to 100% as a target in relation to what we achieved in the lab. Okay, moisture content we will also specify plus or minus, I think, 2% in moisture content. Okay, now once we get that, we have compacted in the field. Then we need quality control to check whatever is compacted in the field is whatever is compacted in the field, we were able to achieve the target that we had set. Okay. So how to do this? We do quality control in the field. Some of the quality control in the field are for determining if the target density and moisture content have been achieved. There are field methods, sand cone method, rubber balloon method, nuclear density method. So sand cone method, and there are also other new methods like the lightweight deflectometer method, CBCD. Okay, there is no meaning to that acronym, just to make it easier. Okay, BCD means an easy method. And then field oven test. Let's have a look at a couple of these. Now, for sand cone method, usually we have a jar with sand. You know the density of this sand. Okay. Now, once we've compacted our surface, we're going to dig a hole right here. Okay. We don't dig a hole. And then we take that soil, we know the weight of that soil. And the soil down from the old. Now we take that soil, go to the lab also and take its moisture. moisture. Okay. Now, what don't we know? We don't know the volume of this hole, right? So we will use the sand here. So we know how much the weight of the sand was here that fills this hole. Okay. If we have a graduation cylinder here, we'll know the volume of this sand. So the volume of sand to fill this hole is the same as the volume of the hole. So then we knew the weight of that soil. If divided by the volume of the hole, that gives us the bulk density. We did the moisture content of the soil here, and we get the moisture content. So we can get the dry density of that soil will be the bulk density 1 plus the water content percentage. So that gives you the dry density of this soil there. So we'll compare this dry density in the field, dry density in the field, compare that to dry density, maximum dry density in the lab, and that will give you the relative compaction in the field. Okay? That will give the relative compaction in the field. Now, that's the sand cone method. For the nuclear density method, we dig a hole, okay? And then the nuclear density gauge has two things. The rod, okay? The rod goes in, it will measure, the nuclear density uses two main sources. One source is cesium 137, and the other one is an americum, I think 200 and something. So these are radioactive elements. Okay, that's what they call nuclear radioactive element. So the cesium 7, I don't know I just forgot it. One would measure the density, and one would measure the moisture. Okay, we'll measure the moisture. So you are able to measure both the moisture and density in situ at the same time, there and there. While for the the sand cone method, you are able to get only the bulk density immediately by calculation. If you know the volume of the hole and the weight, you're able to get. So you have to wait for another 24 hours in order to determine the dry density. So the sand cone method, you're able to get the water content and the density, and then calculate the the dry density in situ. Any question? Any question? Any question, ladies and gentlemen? I want to take questions from you. Let me pause and give you opportunity for questions. Any question up to there? Now, let's follow through an example. Okay, how to determine density from sand. So you have a sand, unit weight of the sand, volume of the cone to fill the volume of the cone, or weight of the sand to fill the cone, measured by given by weight of the cone, volume of the cone. So weight of the jar of the sand before test, weight of the jar of the sand after test, total weight of the soil extracted from the hole, moisture content of the soil from the hole. So you're able to calculate the volume of the hole. Just follow through to be able to get that. Okay. And then the dry density will be weight of the hole or volume of the hole plus 1 times the water content. And then that you are able to, if you follow through this example, going through that, you're able to calculate the relative density. So, for example, if you had a target density of 95 and you get 94, you may consider rework. What do you do in that case? If you had a target density in the field of 95 and you get about 93, what do you do? What do you do? Typing, let me wait for them. Some. Either compact again and change the moisture. What if the moisture? Okay, how do you change the moisture? How do you change the moisture? Increase compaction. Okay, you may use admixtures, but what if you do not, admixtures are not specified? It's just simple, just, rework the place, just scarify this place and then rework it through. Rework it through. Now, my other question is, what if, do you think that if a place passes compaction test, is that enough? Yeah, you probably, let's say you have large area building a warehouse. Okay, you're building a warehouse. Um, Large place, let's say half of Nyayo Stadium field. Okay, half of, yeah, or a quarter of the football field. If it passes compaction, is that the only proof that everything is okay? Okay? That's the question I will ask you. If it passes compaction test, you specify 95, you get 96. Moisture content is within the range. Is everything okay in that case? You wait for answers. Okay, Mohammed says okay. All right, let me get some response. Very good. Francis, that's good answer. Proof rolling. So Francis, how do you do proof rolling? How do you do proof rolling? How do you do proof rolling? Francis Kibera. Kibera, yeah. How do you do proof rolling? Yep. Okay. So yeah, proof rolling, yes. To check for pumping. Okay. Exactly. It's a fully loaded tandem truck. Load this with ballast. Okay, ballast or yeah, ballast. It's a fully loaded tandem truck with ballast. Then just pass a couple of places. So if the place is well compacted, because compaction is only a certain you compacting only probably 9-inch lifts. Okay, all right, but then there could be loose soil down here, right? Because fully tandem, the influence zone exits beyond 9 lifts. It exposes areas that are weak. All right. So if there is no pumping or bleeding, then the soil is well compacted. So, Francis, that's a good answer. Now let's look at the FOT and lightweight deflectometer. Okay. So I said we can use other methods like lightweight deflectometer, field oven, or CVD. So for the field oven, we have an oven mic, uses electricity or battery. So this is fitted with the load cell. You will take a small portion of soil, put in that. It has a load cell and a weight. It measures the soil. Okay, cover that, put it in, and then start it on. It will dry the soil. Typically 5 minutes. Dry the soil. Then you're able to get the oven dry weight and calculate the moisture content of the soil. For lightweight deflectometer, you have a rod and a weight. Okay, the weight is typically 100 newton, dropping about 0.5 meter. The diameter of plate about 0.2 millimeter. This is connected to a load cell right here. So there's a load cell that is connected to. So then, as you drop this, it will measure the load on the plate, the deflection on the plate, and you are able to back calculate the Young modulus of the soil. So the Young modulus is given by a function F, 1 minus V. V is the Poisson's ratio. F will be the maximum force on the plate. D is the diameter of the plate. Delta is the deflection of the plate. Okay, now, the value of F is the place rigidity, 1 for flexible plate and 0.9 for rigid plates. V or mu is the Poisson ratio ranging from 0.3 to 4.5 depending on the type of the soil. F will be the maximum force on the plate. So the maximum force is recorded and the maximum deflection is recorded per time. So that's the maximum force, maximum displacement. Okay, good. So once you get the maximum force, okay, and the maximum displacement, you're able to calculate the Young modulus of the soil. The Young modulus of the soil. So any question, ladies and gentlemen? Are you learning something? Are you learning something? So Humphreys wants me to repeat the light with the deflectometer. Okay. So I talked about the light with deflectometer. This is just you have a plate down. Okay, here. Okay, and this deflectometer has a geophone for measuring deflection, load cell for measuring the load. So as you drop down, it's going to measure deflection of the plate and the load. That is given, in time histogram. Load, and displacement. Load, displacement with time. Okay, because it's producing sinusoidal wave. Okay, all right. Now, the Young's modulus of the soil will be calculated from this formula. F is a function of the plate rigidity. This constant is the Poisson ratio where you perform between 0.35, 0.3 to 0.45. Okay. F would is the maximum deflection of the plate. The maximum force of the plate. D is the diameter of the plate, and alpha will be the deflection, maximum deflection. So that will help you determine the what? The elastic modulus of the soil. And what do we use the elastic modulus of the soil for? What do we use the elastic modulus? Oh, very good. Elastic modulus is related to compaction. Is that the higher the elastic modulus, the stronger is the material. The stronger is the material. Okay. Now, we can also, we can also, even for compacted soil, we can also determine its elastic modulus in the lab. Okay. We can also determine its elastic modulus in the lab. And that's bringing me to the next slide, Francis. Because let's talk about reality. When you talk about compaction, you're only talking about quality assurance of that soil that it has achieved the density that you wanted to achieve in the lab. Okay. That's all. Now, is the strength of a soil only dependent on the degree of compaction? Degree of compaction only gives an indication of the target density with respect to the maximum density that can be achieved. However, when we are expressing the engineering property of any material, we go beyond only the density. We go beyond only the density. Okay? We go beyond only the density. When I am calculating or computing settlement, does density play a role? Partially, yes. Okay. Low density soil implies that that soil has low elastic modulus. High density soil implies the soil has high elastic modulus, therefore less settlement. Low density soil implies the soil has low elastic modulus, hence very high settlement. So Francis, do you understand those facts? Okay? So Francis, what does okay mean? All right. Yep. Any question? Let me continue picking questions for you. Let me pick question for me. I'm waiting for questions. Do it. Okay. If I had a trench like that and I was going to put my foot in here, okay, it does that. Very loose soil, I have to put my foot in here. Or maybe, yeah, I was going to put my foot in here. If this is loose, I would just cut back this and densify this to minimize settlement. What did I do with this? I increased the density. I also increased the modulus of that soil. Yeah. So that does what? That reduces settlement. Any question, ladies and gentlemen, before we proceed? Any question? Any question? Is everything clear as we go on? I mean, give me some thumbs up that everything is clear. Yes, no. At least give me some thumbs up that it's clear or not clear. Yeah, it's clear. All right. Okay. Now, let's continue. Now, the CBD test, we can obtain the modulus of elasticity. CBD test. So we have a 150 diameter, 2 millimeter thick, flexible steel plate. Okay. Now we have strain gauges that are mounted at the back of the plate to record the bending that takes place during the loading. Okay. Now, if the soil is soft, low modulus, the plate bend a lot. Why? Because very low soil, if it deflects more, it takes the shape of that. If the plate, if this is very tough, it bends a little bit. Okay. Now the amount of bending is recorded by the strain gauges and is correcting the modulus of the soil. Okay. Okay, recorded by this now this test, like I told you, like this test can also be performed on laboratory on top of compacted soil. Okay. For example, you can still do soil compaction in the mold. Okay. After weighing everything, you can do the CBD test on the soil on the mold. Okay. To give you the modulus of everything. Or we can still do this on a CBR sample. Okay. Soft CBR sample When you're done doing all your penetration tests, you can do the CBR test on it. Also CBR test. So this is an example of how the test will be presented. The modulus E and the dry unit weight. So that's the dry unit weight curve, and that's the modulus, okay, with the water content. Okay, good. So we don't just compact, we don't just use any equipment or roller to compact the soil.